All right, we're going to be taking a look at this problem here together in a moment. But before we do, on your own, I want you to read through it and then start trying to work it out on your own. Yes, actually write it out on paper, go through it all, and then we'll go through it together. So this would be a great time. Go ahead and pause the video and do that. All right, now hopefully as you work this one through, you started by drawing a picture, because that's a great way to be able to start any of these types of story problems, because then we can attach something to it. And in this case, I got my ladder leaning against a wall, and I could try to get all kinds of artistic about making it clear that that's the wall and all that kind of stuff. But really what I'm most interested in here is the basic shape, as you'll see here. All right, now I got my basic shape. Now I want to start labeling all the numbers that are given to me in the word problem. The first thing we know is that the ladder is 10 feet long. Notice the ladder is that blue line. It's that one that's leaning from ground up to wall. And so the ladder is going to be 10 feet. The next number that I encounter is this one. The bottom of the ladder is moving away from the wall, hence why the arrow is pointing to the right here, at a rate of 1 foot per second. All right, and then the last number that we know is when the bottom of the ladder is 6 feet from the wall. So the bottom of the ladder is going to be right down here from the base of the wall. So that's going to be 6 feet here. All right. What else can we know about this situation? Well, one other thing that we can know about this is going to make our lives a lot easier is that at least if all has gone well with their construction, this wall should be perpendicular to the ground. And so we're going to go ahead and label that as being at a right angle. That's going to help us to be able to write some equations here later on. And the last thing I need to know in order to be able to write those equations is what I'm trying to find. So you'll notice up here the question that's being asked of us is how fast is the top of the ladder sliding down the wall? So that means we're trying to figure out basically this rate right here. Notice that that rate is basically how the length of that side is changing, how the height is changing. And so I'm going to go ahead and label that side. I do want to label it with something that is meaningful, so I'm going to go ahead and call that H. Always use variable names that actually mean something with these types of problems. Otherwise, you run into the potential of forgetting what meant what and mixing up how you plug in your numbers, and it all goes goofy from there. All right, so the natural temptation at this point is to go ahead and now just start writing our equation. And actually, it's going to help us in this case, but it's not going to be quite the final product that you think, as you'll see. So let's jump into that. You notice what we are actually dealing with here. If I take a look at what is getting traced out by all of those measurements, I end up saying that I have a right triangle. And I need to be able to come up with an equation that relates the lengths of all the sides of a right triangle. Hopefully your brain is immediately going to Pythagorean Theorem. So we're going to try using the Pythagorean Theorem here. And so we would set it up as a squared plus b squared equals c squared. In this case, that'd be h squared plus 6 squared equals 10 squared. All right, and so then if I go ahead and solve that through, then that gives me h squared equals 100 minus 36, which is 64. And the square root of 64 then, that'd be 8. So I know that the height then is 8. Well, great. I found out what the height is, but I still don't know how quickly it's changing. Well, in order to figure out how quickly it's changing, we do the derivative with respect to time. But I can't really do that here, because if I did the derivative of this with respect to time, I'd just be saying dh over dt equals 0, which is not the case. Because, of course, if the bottom is going outward, the top does have to be sliding down. So what's wrong with this situation? Why couldn't I do that? It actually comes back to the fact that we used a constant in the derivative where we shouldn't have used a constant. Because if I take a look up here at my original Pythagorean theorem, for instance, this 6 squared, by just doing that and then finding the derivative with the number in there, I'm saying that this length down here is always 6, but it's not always 6. It's only 6 at this moment, but it's changing by 1 foot per second. And so I have to actually leave some variable names in there. So I'm going to go back over to my drawing here, and I'm going to add a little bit more detail. I want to label the other lengths with variable names. So along the bottom, that length that is 6 feet, that's the base of the ladder, how far the base of the ladder is from the wall. You might use B to represent base, but I'm going to use W just because I see a lot of geometry in this one. And certainly H and W are very common for talking about triangles and geometry. All right, and then my hypotenuse there, the ladder, I don't want to use H because I already used H for the height, so that wouldn't make sense for a hypotenuse here. But it is the length of the ladder, so I'm going to use L for that length right there. So with that in mind, I'm going to take my H value and I'm going to write it over here off to the side so I can keep track of it because I don't want to lose track of that fact. And then erase this work because I'm going to need a little bit more room to be able to write this out for it to be nice and clear for you. All right, so I'm now going to go back and do that again, except this time, instead of plugging in all the numbers, I'm just going to do it the variables. So again, Pythagorean theorem. This time, that's going to be h squared plus w squared equals L squared. Now I'm going to do the derivative with respect to time. And you notice that now it actually accounts for the fact that a lot of these things are changing. So now I can go ahead and start plugging values in. So let's go ahead and do that then. So it's going to be 2 times my h value. Now the h I know is 8 because I did that work with Pythagorean theorem earlier. If I hadn't already done that work, I'd all of a sudden be realizing that I had to go and do that work to figure it out. All right, then dh over dt. Remember, that is how quickly the height of this triangle is changing. That's what I'm trying to figure out. So that's still going to stay the variables, the dh over dt. All right, then we just keep plugging in all of our other values. So I grab my w values. Notice that dw over dt is positive here because my width is increasing. And then it's going to be 2 times the length, that's the length of my ladder, which is 10, times dl over dt. Now this is how quickly the length is changing. The length of the ladder at the moment is 10 feet. Is the ladder expanding as it's sliding down this wall? No. Is it shrinking as it's sliding down the wall? No, it's a 10-foot ladder. This is a fixed length. And so for that reason, dl over dt is 0. And this also shows us that back when we were looking at, okay, when we did the derivative before actually naming all these different things, we saw that that w value was changing. So I had to actually leave that as a w. But you can also see that, strictly speaking, you could have actually left this as the 10 because it wasn't changing. And that still would have given you the same value over here by the time all is said and done. But just as kind of a matter of routine, I suggest you make them all variables. And then when you go to plug in the values, you can worry about, okay, which ones are 0 and which ones are actually changing. All right, from here, let's go ahead and actually simplify, do like all the arithmetic that we can here, and then be able to solve it for dh over dt. And so when we solve it all through, we end up finding that dh over dt equals -3/4, and that is going to be feet per second because it's dh over dt. The h on the top is measured in feet, hence it's going to be feet over, and then the t on the bottom is measured in seconds, so it's over seconds. So it's decreasing by -3/4 feet per second. In other words, that means that it's going down 3/4 of a foot, which technically is 9 inches. It's dropping by 9 inches every second, to give you some idea about what this is really telling us then.